Welcome to Plastic Structural Part Design course from BASF. Our instructor is Bill McMaster. With that, let's get started. First slide here, how does design affect costs? If you look here on the bottom, the total product cost, and you can see the design is only costing roughly 5% of the total cost to create a product. So it's a very small percentage. But the influence on the total life cycle costs up here on the top, a good way to look at this is if something goes wrong, what's it going to take? How much resource really to fix the problem? And you can see this influence for design is huge, 70%. So a good example of that is if you decide you have a design project and you need 5 people to do it right and you only have 3, and therefore the design is not a good one at the end, you go in production. A year down the road, you realize, hey, this design isn't working. We need to make it better. Well, now you're going to have to throw lots more people and resources, and it's going to be a lot more difficult because you've got an inferior design to start with, and you're probably not going to want to make all new tooling, and it's going to be very difficult to get a good design. So the bottom line here is this percentage isn't that much, so if you can do it right in the first case, you're going to be better off in the end. Mechanical stress. Those of you that have a mechanical engineering background, this can all be basic in review, but it's still not bad to go over. Basically, any part that sees any stress is going to be, you should identify what the stress is. There's several different types of stress out there. First one being tensile. Good way to picture it is if you grab a bar, a steel bar, and you just pull it in both directions, you're going to put a stress on that bar. Take that same bar and put it in compression, and basically instead of pulling the bar, you're pushing it together. That would be a compressive stress or a force on the bar. Take that same bar now and put it under shear, and you can see what you're trying to do. You're trying to shear it in half, if you will. And the other one would be torsion. You're actually twisting the bar. And the last one would be bending, or what we call flexure right here. And basically, when you're putting a force right in the middle and you're supporting it at both ends, that's bending, or you could actually bend it with your hands as well. Talking about bending, stiffness, and strength calculation. Again, if those of you that have a mechanical engineering background, most of this should be review. It's a fairly important formula. It appears most of the time in the plastic parts that I've been designing in, the maximum stress for a majority of them is in bending. So this really is a key one. And the stress, as we can see in this formula here, stress bending is equal to the moment times the C, which is dimension right here, from the neutral axis to the outer layer there, to extreme fiber, if you will. And then the last one is your moment of inertia. So plug in that formula, that will give you the bending stress. One note here is a lot of people look at C and basically they think it's halfway in the section. And that is not always the case. We can see here in the first one it is the case. For a circular section, it's going to be halfway from the center of the part. Same with a rectangle here, which we're showing here. But if you have a regular shape, say like this T section here, you can see that you actually have 2 different C's. You have a C1 and a C2. But if this is your shape right here, you've got some sort of beam and it's in bending, and if this was your cross section right here, then basically right here would be in compression. This here is being tension. So you could calculate the compressive strength by looking at the bottom, and the top be looking at the tensile strength, or stress in this case. Stress versus strain. We're showing a few different curves here. If you look at the first one here being metal, this would be a classical steel curve. Basically, it's linear, goes straight up, and this is where you get your modulus of the material. And then basically there's a yield here, there's some necking, and then it continues to stretch out, and then finally it will probably break further down the line as it's showing here. A brittle plastic, and that would be, I say, a glass-filled plastic. Basically, it's somewhat similar to that metal curve, but it's not as linear. There is some curvature to this slope here, and then there's a break right about here. And there's no real yield. The break and the yield are pretty close to the same. For a ductile plastic, you can see here, start off somewhat linear, and then you have some yielding at this point in time, and it just continues to stretch out, and it may go a very long time before it actually breaks. Okay, let me just stop here and take a little bit of a break here, showing that some of our resources which you have online that you can access if you're looking for some design information. And you can see here, this is our website. It doesn't actually say BASF. We try to confuse people. You can actually go to BASF.com and actually find this site, but it'll probably take you about 20 or 30 clicks. So if you have the patience, you can do it. But if you don't have the patience, if you're like me, you probably want to bookmark this, and then in the future you can check it out. Again, you'll get a hard copy. But there's a lot of good information. Difficult to see in this view, but we have a snap fit calculator. We have a flow length calculator. There's a cost calculator. A lot of good online tools. And obviously we have a full design guide and a lot of material data. It's a fairly thorough website. Talking about bending, in this case here we're talking stiffness. Basically stiffness really comes from two major components. One would be from your material property, which is your modulus of the material, and the other will be from your moment of inertia, which is really a geometry factor. What shape is the part? What cross-section is it? Is it an I-beam? Is it a tube? Is it a circular section? And that can be calculated. This actually is a very useful formula if you have a problem or a project, and basically you're going to replace steel with plastic, and stiffness is important. Say you're designing a diving board, and right now it's made out of steel, and you want it to be as stiff as the steel. So if somebody walks on that plank on the diving board, and right now they're 200 pounds, if they get on the very end of the diving board, it deflects an inch, then you want the plastic to do the same. You can see here, with the same exact configuration, plastic is going to be 30 times as weak. And that's what this is showing here. So if you want it to be the same, you'd have to play around with the design, the geometry factor, this moment of inertia I. Here we're actually showing an example to do that. If you start off with a present shape, again, say this is your present part and has this cross-section. Again, we'll say a diving board for simplicity's sakes. If the steel part is this, and you want it to have the same rigidity, which is EI, say you decide you're going to make it out of aluminum. Well, aluminum is not as stiff as steel, so what you're going to have to do here is you're going to have to raise the height, and that will give you a higher stiffness. Say you want to make it out of plastic now, glass-filled nylon. Obviously, you'd have to turn this section around in order to be able to stand on it. But in this case here, we had to go up at high. We've corded out. We've got thin sections because for plastic it makes it more cost-effective, and you really can't make a super thick section without causing other problems. So you can see here, just by design, we've made this be the exact same rigidity, and now you can look at what is the cross-sectional area of the steel versus the aluminum versus the plastic. And you can see here the plastic is the smallest, and then if you look at the weight, you can see that the steel is the highest, followed by the aluminum, and the plastic is actually the lightest and really most efficient design. We're showing a fairly busy chart here, but it's actually a very useful chart. You may use this in the future. I know I use it from time to time, and it's very helpful, especially when you have a new project and you're scratching your head a little bit and you're not sure which direction to go. This can give you some guideline. This basically is, the left-hand side is a beam stiffness in bending. And one important note here is to note this is for an equal section area. Basically, what that means is if you look at the I-beam, this I-beam versus circular section at the bottom, basically it's saying if you calculate the area of this circle compared to this I-beam, they're the exact same number. All whatever, 10 of them or whatever number there are here, have the exact same cross-sectional area. And that's a good way now to compare them apples to apples. And you can see in bending, the most efficient design is the I-beam, followed by the C-profile, and you can see going down the line, you know, there's some tubes there that are fairly efficient, and you can see that the solid sections are fairly inefficient in bending. At the same token, moving over to the right-hand graph, you can see this one is for torsion. This is for when somebody is twisting something. And basically, you can see that the different cross-sections here are ranked differently from bending. The tube is the most efficient, the strongest in torsion, whereas the I-beam is actually the weakest, whereas the I-beam was the best in bending. What I use this for sometimes, especially if I have a project or an application where I'm going to use, it's going to see flexural and torsion all in one. If that's the case, you need to do a combination of these two. You wouldn't pick the I-beam simply because the I-beam for torsion is so small, so inefficient. Trying to look at these two, trying to figure out what would be the most efficient, probably would be the rectangular tube. That can be an issue in itself from a molding standpoint, but we'll go into some ways to get around there. But you can also look at, which we'll talk about later, some of the C profiles with some ribbing pattern, which this really doesn't account for. Anyway, it's a good, handy reference chart. I was just talking about the tubes and the hollow sections. This is a good point to talk about gas assist. I don't know how many people are familiar with gas assist out there, but it's an injection molding process where you inject your plastic and then shortly thereafter you inject the gas into the plastic and the gas actually hollows out a section. It's a fairly efficient process, and for the right application it's very cost effective. A couple of quick notes on it though is you can see it's very efficient for the circular cross section. If you got a perfect circle, it'll core that out. You'll have a nice perfect circle in the middle as well, and you'll have a nice uniform wall. But in a lot of cases, that may not be your cross-section. So you look at a trapezoidal type cross-section, and you can see it's not going to core this out uniformly, but you'll still get a good hollow cross-section, but you might have some other issues. You can see here this very thick section is still going to be thick. You've cored it out a lot, but it's still thick in this area here. And the same with the rectangular cross-section. Do get a good core out, but you can see close to the corners are still fairly thick. We're going to talk a little bit about ribs and the efficiency of them and really how to use them to your advantage. There's infinite number of patterns you can use in ribs. Right here we're just showing two of them. This is what we're calling a straight rib pattern, and this one would be a crisscross rib pattern right here. A lot of people would call it an X pattern, or you can actually call it a W pattern, a double W pattern, if you will. Once you decide you want to put ribs on your part, you should figure out what kind of stresses are your part going to see. Are they going to see bending, or are they going to see torsion, or even a combination of the two? If it's going to see pure bending, we'll go back to that diving board. That's pretty close to pure bending, at least if you jump in the middle of the diving board. If that's the case, basically you can have a 0-degree angle rib. And let me show you what we're talking about there. This would be that 0-degree rib. This is that straight rib pattern. So that is very good in bending, but as you'll see, it's pretty poor in torsion. If you're going to have a part that's going to see torsion, a good illustration of torsion would be, we worked on some automotive clutch pedals. And some clutch pedals are totally in line, see pure bending. But if the pedal is offset from the connection rod, that will make the pedal want it, and that whole rod want to twist. And that would be seeing bending and torsion. So if that was the case, basically your optimal rib pattern would actually be 25 degrees or a little bit more beyond 25 degrees. And it would probably be a W or an X pattern, as we'll see here shortly. And you can also see if you have something that's only torsion, you've got some shaft and it's just being turned and you're only seeing it being twisted, basically you want to be at 55 degrees in that range there. And again, if you can put some sort of W pattern or something in there, that may be beneficial, as we'll see here shortly. There's various beam shapes out there. Again, there's probably infinite amount of beam shapes out there, but here's some common ones which we'll talk about. One is the I-beam, which again is very efficient for bending. There's a C-channel. There's a U-channel, just basically a turned around C-channel. There's a hat section. We'll call it the U-channel with flanges. And lastly, the box. Noting that the box you can do with gas assist, or you can start to approach that with gas assist, or if the part's small enough, you can core it out with your molding machine, but if it's fairly long, you're probably not going to be able to do that. So those rib patterns we were talking about, Here's a few of them, trying to give some illustrations on what they would look like. Here's a ladder pattern, basically just looks like a ladder. Here's a W pattern, which no magic here, it's just looks like a W. And then the N pattern, very simply looks like an N. And lastly, the X pattern. So it begs the question, which is going to be the most efficient for your design and your application? We actually did an extensive study, and I believe this was actually done for pedal to figure out what is the best cross-section, most efficient from a design standpoint, so you can use the least amount of plastic and still achieve your stiffness requirements. And you can see here, if you're just going to be in bending, the most efficient is going to be that I-beam with some staggered W ribs or I-beam with W ribs. And you can see that the C channel with W ribs is fairly efficient as well, and then the other ones start dropping off. This is just in summary of what we were just talking about. If you have a bending load, look at an I-shape or a C-shape cross-section with probably W patterns. And 90-degree ribs offer no structural stiffness at all, and that would be that ladder pattern that we talked about earlier. Okay, let's look at torsional stiffness. And here, what's the most efficient cross-section? And you can see here, the U channel with some X ribs is the most efficient. And then you can look at the C channel with X ribs not being bad. And then they continue to go further down. And you can see here, the I-beam is the most inefficient. This is just summarizing what we just talked about. The optimal shape, again, is the U-shaped, and the I and the C channel are not that far behind. And the best rib pattern for torsion is going to be the X pattern. So when you have beams that are under both the bending and torsional load, the hollow rectangular beams offer the best combination of that. If you can't do that from a molding standpoint, which a lot of times you can't, another alternative will be the hat shape with X pattern ribs. This is an interesting chart. One of our questions was, what thickness rib is the most efficient to put in that C channel or in the I-beam? And you can see here, we actually varied it, the ribs, from 30%, 50%, and 100% rib. And we did this with some structural FEA analysis. And you can see here, if you're strictly looking at bending, the most efficient rib is going to be 30%. And again, this is based on the uniform equivalent section. So if you have a 30% rib, you're going to have 3 times as many of them as the 100% rib. So, but you can see here, again, from a strictly efficiency standpoint, the most cost-effective design is going to be using the 30% rib, assuming you can fill that from a processing standpoint. Okay, same question here, but now, what's the most efficient rib for a torsional application? And again, looking at the 3 different type ribs, and this turns around, this is saying that the thicker rib is actually more efficient, the 100% rib. And you can see it for all these different cases, it's consistent. Obviously very interesting, and if you're trying to make your design the most cost-effective, that really can help. So to summarize, if you want the most efficient rib pattern and you have a bending load, you want to use the thinner rib, the 30% rib. Again, if you can fill the part. In some cases, you may not be able to fill it. You might have to go to a slightly thicker, but you want to be on the lower end. Maybe it's a 50% rib. And then if you have a torsional application, you'll want to go to the thicker rib. Designing with plastic, we do a lot with CAE, very beneficial. Before we build a mold or have our customers build a mold, we do a lot of analysis and closely simulate what it's going to be. This is showing some of the tools we have out there that we're using today. For time reasons, I'm not going to go through a lot of the software we're using, but basically say that we're using a lot of software, and obviously a lot of it is very helpful in simulating what actual parts will do. Here's what we do for FEA, and I'm sure a lot of you out there are doing similar things. Here we're showing, this is actually a drill housing. It's probably an impact analysis, and you can see maybe it was being hit here, and you're seeing stresses, you know, in this weak section by the handle here. This part here is this would probably be some sort of fan. Last one I think is clutch pedal. where we're trying to optimize a rib pattern here. Another type of analysis we do is mold filling and warpage analysis, and very helpful software predicting where the best place to gate a part is going to be. Is it going to warp? How do you minimize the warp by changing a wall thickness or adding a rib? What happens when you change some of the processing temperatures? Again, I think a lot of you are probably familiar with this program, but those of you that are not, this is a very helpful tool before you actually, when you design your part and you want to verify what's the best place to gate this part, or is plastic going to fill out your part. A very valuable tool to use. Another program we use, and this would be again for the structural analysis, the FEA, is where do you put those ribs? Where's the best place? And you can see here we worked on this work table, and this was the original pattern that was proposed, and we actually came up with this pattern based on our optimization program. Basically, you use a lot less material. It's much more efficient, and it's a great tool to start with before you build your tool. This is showing the actual process. So you process, you have a material, and then finally you get your part. Throughout that process, this is your flow direction here, and you've got your glass fiber. And your glass fiber, as you can see, is doing a lot. It's a pretty dynamic flow, if you will. Trying to understand that, and again, I've talked about it a little bit. We've actually done some with our FEA, which predicts this orientation and will actually give you a better deflection and stress result because that's what the actual part is doing. All right, and this is showing it in a little more detail. If you're injecting the plastic, what we call the gating, and you gate it here at this end, it's going to give you a certain filling pattern. And this would be, if you looked at a short shot, if you stop your mold at every 1/10 of a second or so, you would see the part filling out just like this. And again, on the outer section, the fibers are actually going to line up with the flow. They're going to line up this way. Right in the center of the part, you can see the fibers are actually going to line up transverse to flow. Ideally, it's nice to have a uniform wall thickness, and I'm sure you've heard that you want to keep a uniform wall, and then the first time you go to design your part, you have to put some features on there, and you're going to violate that. So realizing that in most cases you are going to violate that uniform wall thickness to some extent, you'd like to try to minimize it. So avoid, if you can, any abrupt changes here, sharp transition. It's really going to hurt your flow. It's going to cause stress concentrations. A better way to do it is to do a transition, a gradual transition here. And the best way is to really make it a more gradual transition. That would be the preferred design. The uniform wall thickness, probably can't stress this enough in plastic part design. It really hurts a part if you don't use uniform walls. You can create warpage problems, filling problems. Your part is more expensive. There could be voids in it. So these are some rule of thumbs here. And you can see here, if this was your original design in, say, metal, with plastic, you'd look at it and you'd say, okay, let's core this out. And now overall, my wall thickness there, and now in the center are all about the same. So that would be a good design. Following that principle really is helpful, as any of you probably know if you've been involved designing with plastic. Another design rule is to put proper radii on there. This right here, you can see this, call it a corner bracket, if you will, is a very poorly designed part for a few reasons. One is if, say, you gate it here, basically the part is really just going to dead end. It's going to hit here, and it's going to create some turbulence in this area. The other reason is from a stress concentration, you're putting this sharp corner there, which you should try to avoid. A better way to do it is to put some curvature here. This should be a nice uniform curvature. It seems like the radius is digging in there, and that could be designed even better. Why shouldn't you use sharp corners? Well, you can see here. If this was your part, and this would be your sharp corner right here. That's your sharp corner, the entire length. You put a load right here where it's shown, and where's it going to break? It's going to break right at that sharp corner. So if you can put a radius on there, you're going to increase the strength significantly. And the suggested radius that we'll see here shortly is 50 to 60% of the wall thickness. And the minimum you should do is 20%. And we'll show you on the next slide exactly why that is. This is a stress concentration factor curve. And you can see here from this curve, and this is why we've picked 60%, that the curve starts to level off. When you do your design calculations and you don't include a stress concentration, which most people don't, you're assuming your stress concentration is 1. In reality, it's going to be a little bit higher than that, but if you have a sharp corner, say you're in this high stress area, if a sharp corner could be less than 0.1 even, what your calculation tells you, you're going to have to probably multiply by 3 or even more. That's the bad news. The good news is if you do have a part that breaks and you realize it's a sharp corner, if you just add a radius to the mold, which is a fairly easy thing to do, you can just ride this curve down. Hopefully you're going to be here or even less, and you can see you're going to reduce that stress probably by a factor of 2. So you'll double the strength of the part, and you'll look like a genius. Rib design, one thing you want to avoid is a thick, sharp rib. It can create sink marks. It can create some flow problems. It'll flow down here a little bit quicker than the rest of the section. A better way to do it is to use some thinner ribs and use 2 of them versus 1 thick one. And you'll get the same stiffness, and now from a flow standpoint and a warpage standpoint or a sink mark standpoint, you'll have a much better part. And another way to do it is even 1 taller rib. Again, you'll achieve the same stiffness and you'll have less of these problems. Again, assuming you can fill the length of this rib. There's going to be a limit to filling a super tall, thin rib. So some rules of thumb for rib design. It provides stiffness and it'll give you directional stiffness as well. Some considerations, heating and cooling of these ribs, it's going to make it a little more difficult in building your tool and getting the cooling lines closer to your part. But again, if you don't go too tall with your ribs, that shouldn't be an issue. Tolerances and dimensions. The ribs, they can help your what we'll call warpage or deflection, or they can hurt it. It depends really on the part configuration, but you should keep it in mind. Part weight, you're going to be adding a little bit of weight, but for the amount of stiffness you're gaining, it's usually a nice benefit. And then the ribs can put some molded in stresses into the part. So again, that would create the warpage that we talked about earlier. And the appearance of ribs can create sink marks, which we talked about briefly as well. We've got a busy table here, but it's valuable just to show a couple of points. Just say your present part was this shape, rectangular cross-section and had a 1/4 inch thickness, and your boss comes up to you and says, I need you to double the stiffness of the part, and I don't want it to be too costly or whatever. If you had no experience, you say, I'll just double the thickness. Well, obviously you double the cost and your boss wouldn't like that, but your stiffness would go up a factor of 8, which is nice, and your strength would go up a factor of 4, but again, you double the cost of the part, so your boss wouldn't be happy. So a more efficient design would be to add a rib. So here we're adding a short rib, and then we go further up as we move along. And you can see here, if you do a general rule of thumb, if you can do 3-to-1 ratio, you'll get a huge benefit in stiffness, and your strength will also reduce as well. Rib design, and we talked about that earlier. Thick ribs can create sink marks. And this is one way to evaluate it, is here put a circular section throughout the cross-section, and this one here is thicker. This circle is a larger circle, so therefore you're going to have a large sink mark here. If you can go to a thinner rib, you'll have more uniform circle, and therefore you won't see it as readily. Sink mark depth, we try to analytically study several things, and we looked at the amount of filler content here with rib thickness, and we looked at the rib thickness compared to the base wall of 100 all the way down to 40, and consistently you can see that when you go to the 40% rib, all these different cases, they're all going down. So the bottom line is the thinner rib is going to create less sink mark. In some cases, if you can't go to a really thin rib, and it might be because your base wall is not that thick to start with, so therefore you can't get down to a 40 or 50% wall, you're going to have a sink mark. A couple ways to get around it. One is to put a texture, as we're showing here. That can minimize seeing the sink mark. An even better way is what we call a change in surface or a change in feature. There's actually is still a sink mark in this area here, but the eye just doesn't pick it up because it's not a flat surface. So it's a clever way if you can live with the styling of your part. This here is a boss design, and if you look closely, it's really back to that uniform wall thickness. You can see here, these bosses are violating the uniform wall thickness. And if you go here the correct way, you core these out and you put ribs, you're having a uniform wall throughout, which again is the correct way to do it. And here's some boss design recommendations. And you're going to put a chamfer on here. Your ID is going to be half what your OD is. And again, these are rules of thumb for your files when you print this out. Gusset design, and again, rules of thumb. Basically, it's just showing that your thickness of your gusset should be 75%, even up to 100. And again, you could probably relay that back to a little bit of torsion versus bending. And then the spacing should not be less than 2T, so you definitely want some spacing in there. Thank everybody for participating.